Okay, 14.6 is about another reaction that we've already learned. It's just to review it. It's called the Alkoxymercuration reaction. And this was a two-step process where we added a mercury 2 salt, in this case mercury acetate, in the presence of an alcohol. Your solvent is it's whatever alcohol you use. Whatever alcohol you use is the ether that is formed. So whatever your R group is over here, is whatever R group you use here is the same R group that gets attached onto your alcohol. Okay, and we learned this in the alkene chapter. So remember, we chose this way because this prevented rearrangements. The other way of doing it is just in the presence of acid, and you would possibly get a rearrangement. But in this case, you do not get rearrangements. So the mercury will go on the least, substitute position, and your OR group will go on the more substituted position. So it always gives you the Markovnikov product. All right, and then the second step was adding sodium borohydride, which acts as a reducing agent. Which anytime you see sodium borohydride, remember, think of it as a hydride. Okay, so what this basically does is it comes in, attacks your carbon, and it kicks out the mercury compound and replaces it with a hydrogen. Okay, so here's just a reaction. If you take hex-1-ene, add the mercury hydride, you will get the OR group on the more substituted carbon. So you get the Markovnikov product. Okay, so that was one of the reactions. And these will probably be the words. Again, I got this from the publisher, so I'm explaining it and not realizing what they've already said. So using mercuric acetate with an alcohol, the alcohol react with the intermediate mercurium ion by attacking the more substituted carbon. All right, we already got that. All right, ethers in industry. So in industry, they do not use mercury. They're going to try to find the cheapest, quickest, easiest route to do a reaction. So to make ethers on industrial scale, big scale, is they do a dehydration. They basically take two alcohols and heat it up in the presence of acid, and you basically form an ether. All right, it's what's called a bimolecular condensation. It is a industrial method, not good in laboratory. So if we were doing this on a small scale, this would not be a really good way of doing it. Heating things in acid generally are not a good thing, not a good way to do things. You usually have to do high temperatures. Alkenes are a side product. You can have eliminations. We've learned about dehydration of alcohols. Also, you are heating ethers at very high temperatures. Can you think what would possibly be a problem with heating an ether at very high temperatures? Well, ethers are very flammable. All right, so you can imagine this is not very safe. You can have explosions. All right, but this just kind of just shows you that here's where your water is being formed from over here, and then it's connecting this part to this carbon. Okay. Here's some examples of industry. To make propyl ether, you basically just take propyl alcohol in the presence of acid, and you get N-propyl ether. This N, I don't remember if we talked about this last semester, means it's just a straight chain propyl. All right, the N actually stands for normal. N equals normal, meaning it's not an isomer. It's not an isopropyl. All right, it's just N-propyl. If you do take an isopropyl, notice in that case it's not great. You actually get 100% elimination. All right, because if you remember, the dehydration reaction of alcohols to alkenes is the same reaction. You're heating it up in acid, but usually you heat it up to like 80 degrees, not 140 degrees. But you basically eliminate and you form a secondary carbocation. Secondary carbocations are stable. In this case, you can't form a primary carbocation. We've learned you can't form that. So it really depends on the ether you are making. All right. Another way of doing it is by cleavage of ethers by hydrobromic acid and hydroiodic acid. Okay, this is basically cleaving it. Ethers are unreactive. That's the whole point of ethers. They are very unreactive. That's why they're good as solvents. However, they can be cleaved by heating with concentrated acids, in particular hydrobromic and hydroiodic. Hydroiodic is much more reactive because of the iodine. So let's look at the mechanism. Your book has a pretty good mechanism of it. Basically, the first step is your oxygen is going to protonate, all right, and kick out your bromine to form an oxygen with a hydrogen, 2 R groups, and a plus charge. All right, and then your alkyl halide. So notice your oxygen is very unhappy. It does not want to have a plus charge. All right, so in a way, it's acting as a leaving group. So your bromine can come by then, add to the carbon, and kick this out to form an alkyl halide. All right, notice here's your alkyl halide plus an alcohol. All right, so the halide will attack the carbon via an SN2. That's cleaving an ether. Okay, so if you have an ether and you want to get rid of it, that's how you do it. And your two products are an alkyl halide and an alcohol. Okay. What happens then is that your alcohol can react further because you have HBr in there. All right, it doesn't happen with a phenol. So remember, the last reaction you form an alkyl halide and an alcohol. But now your alcohol, because you have HBr, we've learned this, you can take HBr and alcohol and turn that into an alkyl halide. So your alcohol can react further to form alkyl halide. Same type of mechanism. All right, your oxygen here protonates from your HBr. All right. And then your bromine kind of does an SN2 type of reaction to form your alkyl halide in your water. Okay. Phenyl ether cleavages, however, same thing. You can cleave it in half. You get the alkyl halide from the alcohol, but at this step, the reaction stops because you cannot do an SN2 reaction on an sp2 carbon. All right, so phenol cannot react further to become a halide because SN2 reactions don't occur on the sp2 carbons. All right, so if one of your groups is a phenol on the ether, then it just stops at the first step. This I kind of threw in here, the autooxidation of ethers, because it's just something that is just something that you should just know about ethers. Ethers oxidize with oxygen. If there's oxygen in the air, ethers will oxidize, and they become a peroxide. Okay, oxygens can form peroxides with oxygen in the air. So in the presence of atmospheric oxygen, ethers slowly oxidize to hydroperoxides or to alkyl peroxides. All right, hydroperoxides, I think they have them here, but just to kind of give you right now, is something that looks like this. Okay, a dialkyl peroxide is where you have two alkyl groups. All right, but a peroxide are basically two oxygens. I've stopped because that kind of looks like a face to me. You get the two eyes and whatever. Sorry about that. Anyways, peroxides are basically two oxygens hooked to each other. This bond right here, right, is rather unstable, and it makes explosive compounds. So they are both highly explosive. Ways to avoid them is that if you do a distillation on ethers, is to not to heat until the round bottom is completely dry, because peroxides will then overheat and explode. If you do have a bottle of ethers, they usually have a date that you have to use them by, because the amount of time it takes to oxidize with oxygen is usually a short amount of time. Usually keep ethers in a refrigerator to keep them cold, because this reaction drastically slows down if it's cold. You also try to keep ethers under an inert atmosphere, so an atmosphere other than oxygen, like argon or a nitrogen environment. This way you don't have any oxygen in there. You'll notice the ether that we're going to be using in a few of our labs will have a date on it, and the bottle will be cold because it's kept in a refrigerator. All right. The next section is thioethers. I'm going to quickly kind of do thioethers because it's basically whatever oxygen can do, thioethers can do exactly the same thing. Okay, they're basically, in place of an oxygen, you've got a sulfur. Naming them very similar to ethers, but instead of oxide, you have sulfide. All right, so this would be dimethyl sulfide. Okay, methyl phenyl sulfide. We're not going to worry about this type of naming, but again, anytime you see thio, that implies that you have a sulfur. All right, so just to kind of go over again, thioethers is like an ether but with the sulfur in the middle. The thio implies a sulfur. Naming is very similar. Instead of ether, you use sulfide. Instead of an alkoxy group, you have an alkyl thiol group. So if there was an oxygen here, that would be called an ethoxy group. This is called an ethyl thiol group. That's the only thing that is not the same. You can make these by the same type of SN2 reaction. This is an SN2. It's like the Williamson ether synthesis. Okay, I don't know the synthesized by them using a thiol. I don't know if the Williamson, you know, like thioether synthesis is a name, but it's very similar to the Williamson. The our thiolate ion, this is called a thiolate, does a backside attack and kicks out your bromine. All right, and we're going to stop here, and we'll do the next video on a different one.